Oh, by the way, actually, this is just to show desert is not completely boring. This is actually our neighborhood. It's in Phoenix. Okay, well, actually, before I start the real talk, since Case and Ingo was talking about transverse modes, I was also working on transverse modes some time ago. It's just not what I intended to talk about, but I thought there might be some interesting connection here. Let me just show you. This is a talk I gave 5-6 years back. Okay, so this is actually the multimode VCSELs. I mean, if you drive if the VCSEL is larger enough, you get all those complicated modes. If you do the average, depending on time scale, if you do a slow measurement, you solve, okay, this is the mode you have. But actually, if you do fast enough measurements, the situation is much more complicated. The question is, how can you use this to do something useful? That's Kent was interested in talking about modal, what is it called, modulation? That's a good concept, okay. So, this is again, it is a kind of long time average, you see all the modes. So, okay, so this is a VCSEL. If you take the entire VCSEL output, like indicated by this red disk, this is indicating from the entire output facet. This red line is the time evolution of the total intensity bit. So you got very slow. If you modulate this one, you get whatever, a few gigahertz, the relaxation oscillation frequency. But if you somehow try to avoid the spatial averaging by, for example, taking a small spot like a sampling, spatial sampling, or the simple thing I was actually thinking is, okay, this is a disk output. I put a fiber just off the center. So that I don't collect the entire output, just rather part of the outputs. And actually, you'll see you get all those fast dynamics there. It's not surprising because if you try to collect the part of the outputs, you avoid spatial averaging. So you get those fast modal dynamics. So that if you do this kind of collecting this way and do the high-speed modulation, you get huge, very fast modulation, much faster than you can do with a few gigahertz. This is actually a pretty simple experiment. If you have a 10 micron VCSEL or 15 micron VCSEL, we just try, for example, either roughen the part of the output facet or just use a collection, whatever imaging of fiber coupling, just part of the output. So actually, we did try to see the modulation. This is I collect part of the output. You see their spectrum is a huge resonance here. If you take the total output, of course, you have nothing, just a few gigahertz. This is again there. If I take the half of the outputs, I got this fast dynamics. On this time scale, if you take the entire output, you don't get any dynamics. This is so you can do the small signal modulation. Yeah, this is the one situation. So if you just take the total outputs, the response curve just goes like this, the black curve. But otherwise, you get this one. Well, the problem is the big valley in between. Yeah, so you can actually play with the size of the VCSELs because by increasing the size, this frequency moves closer to this frequency. You actually can merge the valley. You can actually do something useful.
In your case, what does this frequency correspond to? Is it a mode splitting?
Yes, mode beating. It's a transverse mode beating, actually. Yeah, that's actually, you can use the transverse. It's like what I like the modal modulation. By using the transverse mode beating, you can actually do. Actually, Yarif and this guy Ken Lau in the 70s, he proposed to do this longitudinal mode beating, but that's much harder because you can't. Yeah, you can separate them. But with VCSELs, now you can separate the transverse mode. This is actually. So actually, I published a paper. Let's see, 2000 actually about this idea. You can play around the size. So, Ken, you want to do the experiment? This is actually this is a couple of VCSELs, like couple of VCSEL modeling. Actually, well, let's just stop here. So yeah, you can do a lot of things there. I want to go back to my. Actually, by the way, let's see. So my colleague and I have actually a U.S. patent about it. See, Kent, yeah, it's a U.S. patent about modeling. Okay, anyway. Well, we can talk about this. Actually, I think it's interesting. Okay, well, this is something I kind of stop doing. Okay, let's go back to the real talk. Well, just kind of first, before start the real talk, just to, well, Maxi and I, we let's see, it was 15 years ago we were in Tucson. Yeah.
In the past, Jurassic.
Something like 15 years ago. Yeah, so I knew that he was, well, I'm not very familiar with the geography here. So I knew Maxi was in some beautiful island. So I always thought about coming to visit him. So yeah, this, restart, well, this is kind of annoying. Yeah, so in the meantime, Maxi, I kind of stopped doing physics, that's like I taught you. Well, it's because of the pressure of life. So I have to do something that I can, well, support myself. Okay, so my group actually, so after I left Tucson, I went to NASA for like 11 years, 12 years. And so I left NASA 3 years ago, so at Arizona State. So in the meantime, well, I used to be a theoretician. So in the meantime, I don't claim to be an experimentalist, but I became a non-theoretician. Okay, so this is a few kind of projects we've been doing. So the first one is actually nanowires. My group have a CVD lab, can you believe it? I mean, we grow nanowires. So that's one thing. Actually, the silicon photonics is a kind of relatively new project where we grow out some single crystal light emitting silicon compatible materials. So you see the language I use is has nothing to do with physics anymore. So it's pure engineering. Yeah. We do some nano-optics of surface plasmonics for UV generation. And plasmonic lasers is actually the one of the, I guess Ken has heard my talk 3 times in the world. This is the third or fourth time you hear my talk over, I don't know, last year or so, right? Another thing we try to do is electrical injection surface plasmon polariton generation. And there's a little bit of physics here, so we can, yeah. We do a lot of the, I have an optical lab, we have all kinds of lasers, femtosecond and nanoseconds, all kinds of lasers in detectors from UV to 5 microns. So we do a lot of micro-optics, micro-PL measurement, for example. Of course, theory modeling and simulation is still something one of my students is doing. So I have my group is now at 90% experiments, 10% theory. So it's, I don't know if it's unfortunate or fortunate, but that's what I have to do. So let's go back to my talk. Nanolasers, this is something I've been kind of spending most of my time over the last 3 years or so. Actually, it's a little bit longer. So, because we all talk about nanotechnology, nanophotonics, always when you do optics, people, we mention nano, people immediately, what are you talking about? So nano wavelength is so big. What do you really mean? So that's in the process we want to make for like smaller and smaller lasers. So one day you ask yourself, well, is there a limit? At what point you cannot make any laser anymore because of wavelengths or any other constraint. This is actually the same type of giving, I don't know, over the last 2 years, probably giving 20 or something talks with a similar title or slightly variation. Yeah, so the question is, what is the limit? Or whether there is an ultimate limit if you want to make a nano laser. It's actually the founding agents, ARO, DARPA, naturals. You know naturals. Yeah. It's actually, I heard the government say this acronym actually won some award. It's called the nanoscale architecture for coherence, hyper-coherence optical sources or something, I don't know. Yeah, so that's actually we just care about the money. We don't really okay. This is an outline of my talk. I'll give an introduction. I'll talk about surface plasmonic laser, and then talk about surface plasmonic experimental results. Well, if I have time, I'll talk about a little bit of physics. Yeah. Okay. So, their motivation. So this is actually someone claims. Well, this is actually a copy from Cobra. Yeah, you know that Eindhoven. So the Moore's law for photonics. This is a number of components, supposedly per unit area, centimeter, I think, square centimeter. This is timeline over, yeah, see the decades. So this just kind of roughly shows how the integration of photonics actually progressed over time. So where we are now, for example, we are somewhere here. So you see there we have a per unit square centimeter, we have about 1,000 optical devices. So that's kind of the degree of integration for photonics. If you compare, say, the real Moore's law for microelectronics, this is the time, this is the number of transistors. So let's see, per unit square centimeter, we have, what is it, 1,000 devices. For electronics, that was like what, 40 years ago. So that is kind of means that the degree of integration for photonics is what microelectronics was 40 years ago. So there are, of course, a lot of issues why we cannot do as well as microelectronics. But one of the key issues actually is the size. So for passive devices, optical devices like waveguides, we know that we are always limited by the half medium wavelengths. So that's kind of, for example, for single mode fiber, we're talking about a few microns to 10 microns for single mode fiber. For active devices, we're actually limited not only by wavelengths, but also by the amount of gain that is required. So it's like wavelengths and gain. So the gain length required to achieve threshold is actually, well, I'll see whether I have the number there. So we have a wavelength limit, we have a gain length limit, because optical beam has to propagate in the gain medium for at least so long to overcome threshold and all that loss mechanism. So that's another kind of the limitation in terms of size. So I'll skip all the other arguments because I'm concentrating on the size argument. So here are some of those typical lasers. Well, including like what Ken talked about, photonic crystal lasers. So the common kind of features of all those lasers are they are small in 1 or 2 dimensions, but they are large. For example, in this case, this is a kind of disk supported by whatever support, mechanical support. Yeah. So the disk size is quite tens of microns. This is all similar devices. Some of the smaller devices, you can reduce this disk size to about 1-2 microns, but that is the smallest. Photonic crystal laser, of course, active volume is very small, but to kind of achieve this small active volume, you have to make a big disk to support, because we need periodic dielectrical structure. So the overall size is still quite large. So in addition, so all these devices are optical pumps. So which eventually, if we want to integrate, of course, we want to have electrical injection. So the question is, like a lot of questions you can ask, for example, can you actually make lasers smaller than those that what I just showed in the previous slides? Can we make them even smaller? Or what is the ultimate size limit? If you want to push all the way to the limit, where is the limit? Or whether there is a limit? And what about electrical pumping? Of course, that's what we... So that's actually the question. Well, many of those questions were actually asked by this DARPA program, Naturalist program. So the goals of this Naturalist program is to achieve electrical injection, room temperature, sub-wavelengths in all 3 dimensions. That's kind of the laser we're trying to make. Yeah. So that's their why kind of we've been asking these questions. So now let's go back to the laser physics basics. The laser physics for size limits. So while we know that the 2 basic requirements for making any laser. One is the so-called standing wave condition. That's basically what I mentioned earlier. So half wavelengths in the medium. So I call this limit length scale number 1. So this minimum was sometimes called diffraction limit. Well, if your wavelength is 1 micron or 1.5 micron, so your this limit is in the medium. It's about 200 nanometer. So that's kind of already on nanoscale. Yeah, that's not that bad. So, but if you think about the threshold requirements, this is a typical threshold or modal threshold gain. So you can define, slightly rewrite this one, put the length here. So this quantity defines a second length requirement, what I call gain length requirement. Yeah. So that's depending on different pixels or the age emittance. This length could be quite long, from a few microns to about 100 microns. Yeah. So if you compare this length with this length, obviously, wavelength is not yet the limits that we need to work on actively. Actually, the gain length requirement is a much bigger number. So we need to reduce this gain length requirements if we want to make smaller and smaller lasers. So that's kind of a simple comparison, analysis that shows us. So this reducing this L2 is actually a more immediate concern if you want to make a nano laser. Okay, so this is why the options we've been kind of taking. So how do you actually reduce this length requirements? Well, obviously, if this model gain, because R1, R2, we almost push them to the limit in the case of pixels. Oh gosh, how do I get rid of this permanently? Okay, so it's model gain. So we need to have this model gain, the larger the better, because then the L2 will be smaller. So what is model gain? For all of you who are familiar with the semiconductor lasers, the model gain is a product that's the confining factor times the material gain. Material gain is, again, the material parameter. You can not do too much on, except just get the best quality samples. That's it. So really what we can design is to see whether we can maximize gamma, which is a confining factor, which is actually, to some degree, is an overlap with the electronic wave function with optical modes. So the larger the overlap is, the bigger the gamma is. So if you that is what you have to do, and then you think about the options. Then the number one option is what I call semiconductor nanowire lasers. I'll show you some examples what I mean by nanowires, in case some of you are not very familiar with. The second is nanowires with metal shells. In other words, coating or the wrapping semiconductor gain medium with metal. This is why surface plasmonics come into play. So I'll talk about two options. What is nanowire, or what are nanowires? Actually, what I show here, so on the left-hand side, you see this random kind of, not exactly like spaghetti, but it's kind of random orientation. The feature is that this kind of object, they typically have a diameter of about 100 nanometer up to a few hundred nanometer. The length can be like hundreds of nanometer or microns or hundreds of microns or even millimeters. So it can be very long, but it's very thin. So it's kind of high aspect ratio object. So electronically, it not necessarily be quantized electronic, but it's like optical. It's like optical waveguide. It's a mini optical waveguide. Think about that. So you can grow those wires epitaxially from a substrate. In that case, you have different orientations. Yeah. So this is actually you can grow with MBE or MOCVD, or with simple CVD like what we have in our lab. So I can grow those wires with different materials. Yeah. So that's the nanowires. So this is actually the setup in my lab. So it's very simple. It's not like a huge CVD or MOCVD. This is why I could afford to do it. Well, I'll skip the mechanism. If you're interested, we can talk about how they are grown. So in terms of lasers, what are their advantages or potentials these nanowires could offer us? Well, number one, if you can use a single wire to be because it's automatic waveguide, if you can use a single wire as a laser, that is already among the smallest laser you can have, because of diameter, the length, if you can, yeah. And the other aspect is that it's potentially a high efficiency device. The reason is because the electronic mode, optical mode exists in the same spatial volume. So you kind of potentially or intuitively, you think you get a large overlap factor or confinement factor. That's so you get high efficiency eventually, or potentially. So if you grow epitaxially like this indicated here, you can think of this like array of lasers, almost like VCSELs. But it's much smaller, right? Because we have 100 nanometer in diameter. So you got an array of those wires, they're like vertical emitting array of laser arrays. Yeah. Well, this aspect is actually what I think is very important. Because of the small cross section, these wires are very much less restricted by the lattice mismatch between the wire material and the substrate, because the cross section is so small. Or if you grow randomly on a substrate, it's not restricted at all. So you can grow almost any materials on any substrate, basically, because it's not epitaxial connected. So yeah, so those are their kind of advantages or potentials. If you think about comparing, this is a kind of a single wire standing on a substrate compared to the typical edge-emitting PIN double heterostructure laser. You can. This is actually the wave propagates along the wire. This is the substrate. Yeah. Yeah. So you see that the first feature is, of course, the waveguide is comparable or smaller than wavelengths. So that's actually is the number one importance. I'll show you what this means in terms of device operation. And the second aspect is you think about index contrast in a gallium arsenide all-gas system. So the cladding layer and core layer has index, relative index contrast of a few percent, basically, because small index difference between gallium arsenide and all-gas. But because we are talking about the semiconductor in air, so the index contrast is huge, all right? So you can get actually quite big index contrast. You can work out those numbers. Yeah, it could be very large. For example, you have a 3.4 index in air. You can delta n over n average, so over 100%. So the small size, large index contrast puts this nanowire automatically in a different regime than our typical semiconductor waveguide. So this actually changed the laser behavior a lot. So, well, the many other, like, well, one disadvantage is the divergence. Anytime you reduce a laser or optical device, it get more divergent. So that's potentially a bad aspect. So we have to kind of be aware of. Okay, so actually this is the first experimental paper I published. Well, my group published it. That was a few years back because, I mean, for those of you who are familiar with nanowires, the people are doing gallium nitride, zinc oxide, and all the UV range. So when I was at NASA, I was like, this was 5-6 years back, or I thought, well, we can grow some infrared materials. This actually is the first single wire infrared nanowire laser we've demonstrated. This is an output, input, this is optical pump, of course. As you can see, the spontaneous emission, you drive harder, you get lasing. You got multimode lasing if you drive even harder here. Well, the collection is very inefficient because the wire is on the horizontally on the substrate. We collect normal from this, so it's like we have to do a lot of work to kind of improve the light collection. But it's from the spectral features, it's kind of clear that we have a single wire laser. Well, at that time we kind of emphasized the telecom wavelengths. Well, it's probably not that important anymore. Well, okay, so that was, yeah, you can do all the more kind of detailed characterization, but that's just showing this wavelengths drop. Their kind of slope change. This is kind of typical what we identify with laser thresholds. Yeah, so this something is like what I mentioned. This about the advantage of using these materials, nanowire materials. That is, if you grow nanowires with a random orientation on the substrate, you're not limited by their mismatch. Therefore, potentially, you can grow materials with very wide range of the band gap change, so that you can achieve very many colors on the same substrate. This is actually what we did. This is quite recently. A paper, well, eventually got published early this year, well, last year actually. So this is actually the real color of the substrate we grow, actually. This is the real color, it's, yeah. And it's like you just take the substrate as sample out of your growth chamber, you just shine a laser on it. So the color change is actually because the semiconductor band gap is changing from the left to right. Yeah. And this is actually the micro PL. We kind of scanned like about 15 points along the length from the left to right. As you can see, when you scan from left to right, the band gap changed, or the band gap emission changed from about 500 nanometer to about 700 nanometer, over 200 nanometer range, over just one substrate. That's about 1 centimeter long. So the 1 CD grows. Yeah, this is something obviously you can't have this one in the epitaxial, the traditional thin film or quantum well growth. So the interesting thing was that we just, because this is optical pumps, so if you drive harder, actually what you see is that every point actually becoming lazy. So as it's kind of indicated here. So what you have here is kind of almost like a spatially tunable laser over 200 nanometer range. And that's something obviously very exciting to have. well, this is of course, this is a optical pump. So, well, it will be a big challenge actually to make this electrical injection, but that would be great. So, over 200 nanometer tunable, spatial tunable, and this is even more kind of impressive. So, after we got this, well, I didn't mention the materials we used was from cadmium sulfide to cadmium selenide. Yeah. So when we got this one from 500 to 700 nanometer tunability, and then we thought, well, we have our program supported by Army Research Office. So we, the guy said, oh, can you do UV? I said, sure, yeah. And you look at the band gap, well, the band gap versus lattice constant, the chart, the standard semiconductor chart, you look what other wider gap materials that you have. And quickly realize that the zinc sulfide, for example. And zinc sulfide can be composition graded with cadmium sulfide. Wow, this is really, they don't give you an option to kind of create it. Okay, so what we had earlier was from somewhere here, from 500 nanometer to 700 nanometer. So now what we did, we added zinc sulfide. So now we see what, this is again the 3 samples with real color, so it's band gap emission. So now what we have is from blue, actually it's like in UV range basically. 350 nanometer all the way to 700 nanometer. This is again a single substrate, all the single CVD growth. Yeah, I won't explain, well, I won't waste time to tell you how we grow it, but if you're interested, we can talk about it. So this is we took like over 40 points along the length. As you can see, the micro PO, as you move from left to right, you see the PO peak kind of continuously changing. Actually, what is surprisingly interesting is actually, in a wide gap range, typically wide gap materials always have the mid gap emission, the green yellowish emission, because of the mid gap defects. But because we optimize the growth condition, actually you see even for this range, the mid gap, which would be somewhere here, actually is minimum. So actually it's kind of an indication because the growth we use actually, so the growth condition actually allow you to minimize the defects emission. So this is like quite interesting materials.
Sorry, so you say that the wires are randomly orientated in the sample, so
yes.
So they emit in all directions.
Yes, yes, I didn't know. Yeah, that's a good question to ask. So because we have wires kind of randomly on a surface, basically, if you measure the light emission from one point, whichever wire at that point is the largest will first lays, of course. And then basically you measure light kind of scattered from the ends, actually. So that's yeah, eventually you want to do a better job than that, but that's just the first demonstration. Actually, we fought with the referee for almost a year. And just, well, I'm not sure if you ever heard of this journal. This is the first time I published a paper in this journal. Do you know ACS, what ACS stands for?
American Chemical Society.
Okay. I learned this very recently, what ACS stands for. Yeah, so American Chemical Society, Nano, ACS Nano is quite a good nano journal, yeah. And so yeah, this just actually, the paper was just accepted a few weeks back. Yeah. This is actually something interesting. So our original motivation was to use this as a tunable. So okay, so the interesting aspect is if you can make this tunable laser over, let's say, 350 nanometer to 700 nanometer, that would be great, all right? I mean, so that was our original motivation to make tunable laser. But once when I showed this material to one of my colleagues who work on solar cells, they said, "Oh, this is a great solar cell material." I actually spent some time to design a special solar cells actually I'll just show you, well, skip all their arguments about why you need multi-junction solar cells. But here's their crazy idea about solar cell. This is a completely, well, if you're not interested in solar cell, you just can take a break. This is what I claim to be a full spectrum solar cell. Well, you can actually use on-chip spectrometer if you want. Okay, so this is the basic idea. This is my composition graded semiconductor nanowire. I can pattern my substrate so that I grow this. This is the length of the sample. Yeah, I subdivide it into how many subcells by patterning their substrate. That's straightforward because this grows rely on the catalyst. If you can't, where you don't have catalyst, you don't grow wires. For example, you subdivide this into, let's say, 10 cells. Now, well, this is a kind of the further device specification of this sample. Now, it's like how many subcells. If I can do the lateral PN kind of contacts laterally. So what I do then is I use, let's see, the sample is just a grating, for example. That was I thought initially I just need a grating. So the when the solar light, white light comes in, the grating was, well, split the colors in different bands, wavelength bands. So what I do is I just optimize the division of the subcells so that the right wavelength window or bandwidth go into the right band gap intervals. That's all I just need to. So why that is important? Well, that is important because for solar cells there are two major losses. The one is the thermal loss. That is when the photon energy is larger than band gap, you get a lot of thermalization, so you generate a lot of photons. That's a heat. You heat the solar devices, you waste a lot of solar energy. So that's one of the problems. And the second problem is that if the photon energy is smaller than the band gap, you get transmitted. So solar photons energy are wasted. By kind of dividing this, so matching the absorbing material with the right wavelength band, you kind of optimize for both to minimize their both important loss mechanism. So that's why this people work on multi-junction solar cells, like a staggering, like 3-4 junctions. But the problem with the staggering multiple junctions is that you have to find 3 right band gaps on a given substrate, which is very difficult. Number one. Number two, you have to current match all these different junctions. In this case, actually, because each kind of lateral junction is separate, basically. And actually, you can do a kind of, well, potentially you can do much higher efficiency. And so when I showed this, I thought this is almost, at some point I was almost like ashamed of showing this to anyone. And so we had an internal workshop. I mean, I showed some small circle. There was a guy from the University of Arizona. This guy, Ray Kostick, I'm not sure you know him. He's a diffraction optics expert. And his lifetime is devoted to make something called dispersive concentrated solar cell. He actually uses the holographic technique to make thin film gratings, almost like gratings, for solar cell applications. Actually, from him I learned actually the dispersive concentrator solar cell PV is actually a big community by itself. So after talking to him, I kind of started to show this slide to kind of wider audience because I thought, okay, it's not that crazy after all. So that's actually, so recently I kind of showed to some experts, like including the guy from Luque. You guys know him as a Spanish, in Madrid, from Antonio Luque's. Yeah. So actually in Berlin in August, I showed him this, and he was actually very intrigued. He was asked, well, a lot of questions. So now I kind of feel that it's not that crazy. So we actually are going to get some funding to do this work. So this is again what kind of distraction. It's not really laser. Okay. Back to nanowires. Some of you guys are interested in the spatial patterns. This is actually one of our nanowire lasers. The cross section is a kind of hexagonal. This is actually a cadmium sulfide nanowires. And so this is all the modes we get. You see the very broad band, is that right? This is actually mostly, this is an interesting material. So the diameter is 1.7 micron. It's smaller than typical VCSELs, for example. But you see the kind of modes, very complicated. So we got so many peaks, you see. Every peak you can find, we actually, this is simulation, of course, yeah. We don't have this high spatial resolution imaging, yeah. So we just kind of, because experimentally we measure all those peaks and we try to understand them. We just did the simulation just to, for example, each peak position, what are the modes? Yeah, those are all the modes that we have in those frequency range. We can match a lot of those modes actually. As you can see, the transverse pattern is just unbelievably complicated. And well, this is again, it's yeah. So another interesting thing is that this mid-gap emission band, this is actually the band age. So this, we purposely introduced some defects or surface states. So that's actually the frequency range here, the gain materials are concentrated on the peripheral of the wire because of the surface states. It's a ring, kind of annular structure, the gain material in this frequency range. The band gap, of course, is uniformly spread everywhere. So you can use this one, you can play around with overlap with the game tutorial with modal pattern. Actually, selectively kind of increase one of those or few of those modes. And this is, again, I won't spend too much time on this one. Let's see. How much time I have? 5 minutes?
You go ahead.
Go ahead.
No. I mean,
10 minutes at least. 10 minutes.
10 minutes, okay. Well, I have to skip some material. Okay. Well, I have slides for next 2 hours if you. So, yeah, okay. Okay, so let's kind of get back to one of our arguments of using single wire to make lasers was the size. So the question is, what happens if you shrink the wire diameter? Well, obviously, one consequence is that they're leaking the optical mode. The optical mode would leak outside of the wire, basically. So the simple question would be, okay, if we coat the wire with metal, would that help? I mean, that's actually, we came to the surface plasma confinement of the semiconductor wire. This is why it's going to just go quickly about what is surface plasma. So this is actually the dispersion curve K omega, that's a waveguide. So this is, of course, the straight line uniform dispersion K, well, this is what we all are familiar. So this is actually so-called surface plasma and bulk plasma. So they are just kind of frequency fixed, almost no dispersion. Yeah. So when, of course, in a real waveguide, when you, let's see, coat the semiconductor with metal, you get this metal, the surface plasma or the plasma excitation in the metal that couple with optical propagating modes. Yeah. So when that happens, of course, those crossing, of course, we know it's never happened. So actually what you have is actually this anti-crossing. So this is actually the so-called surface plasma polariton. This is the so-called bulk plasma or plasma polariton. So skip this one. So what we want to do is actually, this is, in this limit, you have a typical standard cavity laser. In this regime, what we call, there was a guy, Mark Stockman, he was actually here, Spacer. So I think most of the regime we are working on is actually the surface plasma polariton laser. That's what we tried with metal, cavity, semiconductor gay medium. Okay, so that's, I'll just show you the results actually. I'll just skip all the physics arguments. Yeah, I'll skip this too. Okay, so this is actually, around like, 3-4 years back, when we were studying the feasibility of the coating the metal, coating the semiconductor with metal, see whether this is a realistic solution. So we did a lot of simulations, thought this is feasible. We don't know whether it's exactly possible, but we thought it's at least not that crazy, so we should try it. So when we were trying to make the structure, so it's basically a semiconductor nanowire, let's see, 200 nanometers, we want to coat a layer of metal to make a metallic semiconductor cylindrical waveguide. Yeah. So we tried to do that. Actually, I was visiting their technical university of Eindhoven. Before my visit, actually, there was a paper published by this guy, Martin Hill. So that was actually my beginning at the ASU, Arizona State. I was looking to hire people, so that wherever I traveled, I would spread the flyers that I'm looking for postdocs, whatever. And so one day, well, before my trip, the Martin Hill's paper appeared in Nature Photonics. It's something like this device. So when I got there, I was asking Martin, I said, well, whoever in your department is interested in doing a postdoc at Arizona State would be great. And Martin told me, well, I said, well, if you're interested, I'll be interested in working with you. that turned out to be a very good, fruitful collaboration. So Martin joined my group at, early 2008. So actually, after Martin came to our group, actually, I would not be able, this is a very complicated structure, fabrication-wise. So Martin really kind of did all their fabrication work. So this is actually their smallest laser we've made so far. And so what is shown here, this is an electron micrograph image of their semiconductor pillar structure. So what we did was we started with a wafer. we etch this semiconductor pillar, like either a circular pillar or this rectangular pillar. Because the goal of this DARPA project is to make sub-wavelength laser. So we thought, okay, let's just forget about the dimension in this direction or this direction. Just squeeze from one direction to see how thin we can push to make the device still laser. And so the smallest thickness we tried was this one. The semiconductor is about 80, 90 nanometer thick. It's thin, yeah? So we coated with a dielectric silicon nitride on both sides, and then we, like a 20 nanometer silicon nitride on either side of this pillar. And then, of course, we evaporate silver. Basically, it's silver covered. So this is kind of schematically shown here. This is the P contact, N contact. This is semiconductor pillar. This is the active region. So the black region is silicon nitride. So this is what we call metallic catalyzed laser. So this is actually the thinnest one we can try to laser, about 90 nanometer. This is the spectral at different pumping level. This is, I think it's no doubt this is a laser. I mean, it's laser. So, this is of course low temperature at this point, but it's electrical injection, which is quite significant. If you kind of figure out what is the total optical thickness in this direction, so we have about 90 nanometers indium phosphide or yin gas, like 3.1 index, plus, like assuming silicon nitride has index of 2 layers on either side of 20 nanometer each. So you add those up, you get something 360 nanometer optical thickness. Well, there's some slight metal penetration, but metal has a very low index, like point something. Yeah, so you can almost ignore it, add a few nanometer optical thickness. If you compare this one with the half lambda, the half lambda is 670 nanometer. So the optical thickness of this device is only 360 nanometer. So we're talking about the optical thickness being half of the half lambda. So that's really something we were very happy. Again, we followed for a very long time with their Nature Photonics. We thought, well, this is kind of a trivial extension of the earlier work, so this paper was rejected, so eventually we published Optical Express. And it was good, actually, so right after our paper was published, there were 2 Nature papers by the group, this guy, Modulation, you saw him, yeah, Michael Modulation, and by their Berkeley group. And they were all later than our paper, but they published in Nature, which is, I don't know. When I show you our spectrum, you compare with their spectrum, I don't have to say anything. But I won't show that spectrum here. Huh? Okay, so this is what let's skip this one. I think time is up, right? I'll skip, there's some, I guess probably not that great. Okay. Okay, I see what I want to say. So maybe just one message here is their metal semiconductor integrated structure, all their waveguides or composites now can become very important. Number one, for making nanophotonic devices, because there is no any other mechanism that we know that would allow you to shrink the effective wavelengths that much to make substantially sub-wavelength devices. This is why metal structures become so important, or plasmonic effects become so important, number one. But the problem is we know metal has a huge loss. So the question is whether you can find the right trade-off where the loss would be tolerable and where the metal allow you to reduce their size to sufficiently small. So it's kind of trade-off between the size and the tolerance of the metal loss. And so what we believe, based on our research, both theoretically and experimentally, we think there is a good trade-off you can do. Actually, you can make the substantially smaller nanophotonic devices. I guess I haven't answered my question, right? The title of my talk. I don't know whether, okay. My short answer is there is no principal limit to how small you can make a device. That's a short answer. Actually, if you were at this winter topic conference this week, I'm not sure if any of you went there. Listen to this guy Mark Stockman. There's this thing called Spacer. If you are talking about Spacer, then there's absolutely no limits. You can, in terms of how small you can make a device. Okay, good, thank you. Well, actually. It's actually my students, postdocs, collaborators. Yeah, that's obviously very important. Yeah. Thank you. Any questions?
Okay, thank you. So, questions?
You mentioned this trade-off between losses and certainly size that you can achieve. So, with, for example, your technology, what would be a realistic trade-off as a minimal size for such devices?
I mean, you said realistic or what?
Yeah, realistic.
Realistic. Well, okay.
Not fundamental. Because I guess that it will be realistically the losses which determine that, right?
Realistically, yeah, this is. I mean, to be honest, I can't give you a very definite answer. What is realistically? It all depends. The answer is a function of the funding, for example, or whether you can get good enough students. I mean, it's not really what I'm trying to say is not principle.
So, what is the major loss mechanism?
It's a metal loss because the metal you excite free electrons in the metal, and that just becomes Joule heating. So that's a major loss. The loss is huge. So I have a slide that shows loss is unbelievable. I mean, loss is huge. But we found there's an interesting piece of physics where you can. I mean, that physics is actually interesting, but I have to skip it. Okay, well, whoever else can ask questions for the meantime.
You said that in your book you still do 10% of theory and modeling.
Yeah.
Now, which are challenges and opportunities of modeling in nanolasers?
There are a lot of there. Actually, if you do the 3D FDTD simulation, a lot of issues you can study actually with metallic or waveguide. Adding real plasmonic effects. There are a lot of things you can do. There's metamaterials, there's nanolasers, nano-waveguide, a lot of things you can do actually. Actually, I didn't show, there was I just wrote a tutorial paper to this, what is German journal called, Physics Status Elite. Yeah, that's a tutorial, I mean, I talk about all the aspects. I can send you a paper, yeah. So that's, a lot of, actually in terms of modeling, simulation, or theory, there are a lot of things. Even actually, one of the interesting physics or theory that you can do is actually, so when you put the quantum dots, for example, or even two-level atom, in a close proximity of a metal. And so the typical dipole interaction, all the standard interaction, light matter interaction models would not be valid. I have a postdoc from Japan who spent 1 year working with me. Eventually, by then, for 1 year, he didn't finish the model, so he didn't publish anything. So there are a lot of physics actually you can do there. Yeah.
Any other questions?